Okay, Assalamualaikum warahmatullahi wabarakatuh. So we are going to solve a heat equation of del u del t equals to del squared u del x squared, where x is 0 to 1, and we know that from this information that L is equals to 1, the length of the subject is L equals to 1, and for increasing t. Okay, the initial conditions is given by ux at t equal to 0 is equals to x, while the boundary conditions at both ends u0t equals to u1t and equals to 0. Alright, okay, we're going to start with the first step, step 1, where we're going to separate the variables. Alright, okay, as we understand that when we solve the heat equation, we are going to have two independent variables where the independent variables are x and t. So x is for the dimension, the spatial variable, and t is for time variable. So we're going to separate the variables. We're going to start with the assumption of the solution of uxt, because if we can separate the variables, so the solution of uxt is equals to the solution of x times the solution of time. Alright, then we're going to put this assumption into our PDE. So in the left hand side, we have first derivative of u with respect to t, therefore we're going to have xt prime, and equals to, in the right hand side is the second derivative of u with respect to x, therefore we're going to get x double prime t. We're going to divide both sides with xt. Okay, then what to do next is we can just simply cancel out x variable in the left hand side and t variable in the right hand side. Therefore we're going to obtain two ordinary differential equations, and we can see that this PDE is a separable equation, since we can separate t variable in the left hand side and x variable in the right hand side. Okay, to preserve the equality, we're going to let this equals to a constant k. Alright, therefore we can reduce the PDE into two second order differential equations. Okay, so as you can see that is the first order differential equations for time variable and second order differential equation for spatial variables. Okay, and three possibilities of value of k. Okay, when k greater than 0, we're going to let k equals to lambda squared. When k equals to 0, and when k less than 0, we're going to put that k equals to minus lambda squared. Alright, this is for the first step, where we have we separate the variables and we reduce the PDE into two ordinary differential equations. Right, then the tips. One of the tips to solve PDE is to solve the spatial variable, okay, by applying the boundary conditions of spatial variable, okay, before we look into the solution of time variable. Okay, this is due to in few cases, okay, because we have to consider three cases of values of k. Okay, so we can see that by solving the x variable, first we can reduce the complexity of the calculations. Okay, where in few cases we can neglect the solutions of the uxt. Okay, in the corresponding or in the particular cases. Alright, so step 3, since we need to solve the spatial variable, so we need the boundary conditions for spatial variable. Okay, step 3 is to set up the boundary conditions. Okay, so boundary conditions given in the equation is u0t equals to 0 for the first boundary condition. We're going to put this into our assumption that at x equal to 0, okay, while t remains t, is equals to 0. Right, we cannot let t equal to 0, otherwise partial variable, otherwise is trivial solution. Therefore, we're going to let x0 equals to 0. Okay, for the second initial condition, u1 t equals to 0, we're going to put into our assumption that at x equals to 1, while t remains t equals to 0. Again, tt cannot be equals to 0, therefore x1 equals to 0. So this is the first boundary condition, this is boundary condition, and this is the second BC. Okay, why we do we need two boundary conditions? Because we are solving second order ODE for x variable. Okay, now we have the equations, the second order ODE of partial variable, we have the boundary conditions, then we can solve the partial variables of this the second order differential equation of partial variables. Okay, for the for all cases, k positive, k 0, and k negative. Alright. Okay, so we have step 2 where you have to consider solution for 3 possible cases. Okay, we'll start with case 1. Okay, another tips is you solve k starting from k equals to k positive, then k 0, then the last value of k is when k negative. To solve for case 1, k greater than 0, we're going to let k equals to lambda squared. Alright, so if I can just rewrite the second order ODE of partial variables, we have x prime minus kx equal to 0. We're going to put in the lambda squared, k equals lambda squared into the equation. Okay, this is similar, the solution of this homogeneous second order ODE is similar to what you have learned in chapter 2. So we have to write down the characteristic equation. Okay, so this is m squared equals to lambda squared. Alright, then m equals to plus minus lambda. So when you look at the solution, you can see that the roots are real, but real and distinct. Okay, therefore the solution of x is equals to a exponent lambda x plus b exponent minus lambda x. Alright, then we're going to apply the boundary condition. The first condition says that at x0 equal to 0, when we put 0 into the equation, we're going to get a plus b equals to 0. Okay, then x1 also equal to 0, so when we put x equals to 1 into the general solution, we're going to get a exponent lambda plus b exponent minus lambda equals to 0. Okay, so from the first equation, a is equals to minus b. Then we're going to put into the second equation, then we get negative b exponent lambda plus b exponent minus lambda equals to 0. We factorize b, we're going to get b negative exponent lambda plus exponent minus lambda equal to 0. Therefore, b is equals to 0 because exponent negative, whatever in the bracket here, they are constant. Okay, so 0 divided by any constant is equal to 0. When b equal to 0, therefore a equal to 0. The solution of xx equal to 0, therefore the solution of uxt also equals to 0 because uxt is the solution of x times the solution of t. Since the solution of x is 0, so we don't need to solve the t variable. Okay, since the solution of x gives us a trivial solution, so therefore we're going to neglect the solution for case 1. Alright, then we move to case 2. When k equal to 0, we substitute into the second order ODE. We're going to get x upper prime equals to 0, so m squared equal to 0, so m equals to 0. Even though you have the solution, when you look at the answer for m, you only see one value, which is 0, but because we are solving quadratic equation, so these roots are real but repeated. Okay, therefore the solution of x is equals to a plus bx. Okay, we substitute the first initial boundary condition. a equals to 0, while when we put the second initial condition, we're going to b equals to 0. Again, x equal to 0, therefore uxt for case k equals to 0 is equals to 0. Trivial solution. We're going to neglect the solution for k equals to 0. Therefore, we have to solve the t variable since the solution of x is a trivial, give us a trivial solution of the solution of PDE when k equals to 0. Okay, now we expect that we're going to get the solution in case 3. So case 3 is when k negative, k equals to minus k negative, k equals to minus lambda squared. Alright, we're going to put into the second order ODE, then we're going to get x over prime plus lambda squared x equals to 0. This is the characteristic equation of the homogeneous second order ODE. M squared plus lambda squared equal to 0, m squared equals to minus lambda squared, therefore m is equals to plus minus lambda I. Alright, you can see that when k less than 0, the roots are complex conjugates. Therefore, the solution of x is equals to a cos lambda x plus b sin lambda x. Alright, for the first boundary condition, when we substitute x equal to 0 into the general solution of x when k is negative, we're going to get a equals to 0. Okay, when we substitute x equals to 1, we're going to get a cos lambda plus b sin lambda equals to 0. Okay, this term is already 0 because a equal to 0, therefore b sin lambda equals to 0. Okay, since we want to avoid the trivial solution again in case k negative, okay, so we cannot simply let b equals to 0, since if we let b equal to 0, then again we're going to get a trivial solution. Therefore, this is not what we are seeking for. Okay, we don't want trivial solution, we don't want no solution of the PDE. Therefore, the only solution is when sin lambda equals to 0. Alright, so if you can just recall that sin lambda equal to 0, we can find the values of lambda. Okay, if you can recall in the Fourier series chapter, we always say that sin n pi is equal to 0. It's not we always say that sin n pi equal to 0, but when we sketch the sine function, the sin n pi when n is 1, 2, 3, 4, 5 always give us equal to 0. Therefore, if we can compare the angle, so we can see that the value of lambda n is equals to n pi, where n equals to 1, 2, 3, and etc. Okay, therefore the solution of x is equals to b sin n pi x. Okay, since we have written it in series, okay, then we just need to put the solution of x, nx is equals to bn sin n pi x. Alright, now there is a necessity to solve the time variable since we have the solution of the spatial variable. Okay, now we want to rewrite the solution, the first order ODE of time variable. Okay, since this is when the case when k is negative, where we let k equals to minus lambda squared, when we substitute into the first order ODE of time variable, we're going to get t prime plus lambda squared, t equals to 0. Alright, okay, how are we going to solve this? Alright, so this is actually a linear equation. Okay, if you can just look at the solution, the linear equation in chapter 1, when we solve first order ODE, okay, we'll find how to find the general solution of t variable, okay, for this type of equation. Alright, okay, but I'm going to just simply show you how to do it. Okay, we have t prime equals to minus lambda squared t. So t prime is actually dt. So we rearrange. You can simply separate this. Okay, this also this equation is also a separable equation, so we can separate into both into only the capital T variable in the left hand side and the small t variable in the right hand side. Okay, we solve this is ln t equals to minus lambda squared t plus c. Alright, so when we exponent t equals to what we call it, okay, d exponent minus lambda squared t. We know what is the series of lambda, so we're going to write down as a series. See, this is equals to exponent minus n pi squared t, right? Okay, so we have the solution of x, we have the solution of t, so therefore the solution of uxt is equal to en, the solution of x sine n pi x, okay, times the solution of t dn exponent minus n pi squared t. Alright, since we already put this in series, so we have n equals to 1 to infinity. Alright, so we can reduce the unknown of, because here we will see that there are two unknowns, bn and dn. So how can we reduce the unknown? bn is just a constant, dn also a constant, therefore a multiplication of two constant equals to another constant. So you can just simply write it as n equals to 1 to infinity bn sine n pi x exponent minus n pi squared t, where bn is equals to bn times dn. Alright, okay, now we have the solution of uxt. Okay, so this is where we're going to apply the initial condition. Okay, since we still have the one unknown constant, which is the bn, then how can we find the values of bn? Alright, so this is where we're going to apply the initial condition. So uxt is equal to n equals to 1 to infinity bn sine n pi x exponent minus n pi squared t. Right. Okay. Initial condition says that at t equals to 0, the function is x. Right. So we're going to apply this initial condition. This is when t equals to 0. We're going to substitute into the uxt. So we're going to get ux0 is equals to, okay, so if I can just give you the direction of where can you put this t equal to 0. So exponent 0 is 1. Okay, therefore the series, when we substitute t equal to 0, becomes bn sine n pi x. Alright, and this is equals to x. Where do you get this x? This from the initial condition that says that ux0 is equals to x. Okay, now this is familiar equation, okay, where you have seen this in Fourier series chapter. Alright, in order to find bn, where this fx is equals this x is actually the fx, right? Okay, therefore bn is equals to, we're going to use Fourier sine series. Why? Because why Fourier sine series? Because we see that you are solving the coefficient in front of the sine function. Okay, therefore it's a Fourier, we're going to apply, or we're going to use the Fourier sine series formula, but it says that bn equals to 2 on L 0 to L fx sine n pi x over L dx. Okay, we know that L equals to 1. Okay, so this is 2 on 1, 0 to 1, fx is x, then this is sine n pi x dx. Okay, when you look at this, then you see that we need to use a tabular method in order to find the in order to solve the integrations. So we have this tabular method where the left column is for derivative, for the right column is for the integration. I'm going to choose x to as a function that we have to differentiate. Differentiate x is 1, differentiate y is 0, and the function that we need to integrate is sine n pi x. First integration will give us negative cos n pi x over n pi. Okay, second integration is sine n pi x n pi squared. Alright, cross multiplication, don't forget we have to put the sign. Alright, so this is equal to 2. Alright, first term is negative x over n pi cos n pi x, and the second term is plus sine n pi x over n pi squared. Okay, where the limit is from 0 to 1. Okay, substitute the limits. When we substitute the first limit, the upper limit x equals to 1 into the resulting integration, what you get to negative cos n pi over n pi, okay, plus sine n pi over n pi squared, minus, when we substitute x equal to 0 into the equation, then we get 0. First term is when x 0, the first term becomes 0, the second term sine 0 is always 0. Okay, then okay, cos n pi is equals to minus 1 to the power of n, sine n pi equals to 0. Okay, so our final answer is negative 1 to the power of fn plus 1 divided by n pi. Alright, okay, therefore our solution, since we have obtained the n equals to 1 to infinity, bn is 2 negative 1 to the power of n plus 1 divided by n pi. Okay, sine n pi x exponent minus n pi squared t. So this is the final solution. Alright, that's it. Thank you.